Okay. Hello. Okay. All right. I'm sorry. I don't know what happened. But I had unstable internet, so I just came back. Hopefully, just last a few minutes. And thank you for being patient. So let's move. Kind of just perfectly matching each other, patch it up. So the total would be 10,000. On the other hand, if we combine the second and the fourth number, 92 plus 108, that would give us 120. So both numbers are fairly nice. 10,000, then 200. That's the final result. So this is a very straightforward application using essentially commutative law and associative law to rearrange the order of your addition, and they're equally spaced. So in this case, how do we group them properly to take advantage of the underlying property? So summation. And that's exactly what we will do here. So 129, 126, 129 plus 132 all the way to 234, I believe. Yes. So the idea is that if we combine the first one and the last one, and the second one and the second to last one, you can see that because the first number goes up, and the second number actually goes down from the very last one. So one is going up and one is going down. They happen to cancel out each other. Therefore, the sum of each pair should be the same across all those pairs. And the total summation problem becomes adding a group of numbers that are all equal. Therefore, it became a multiplicator for this type of problem yet. So it's worthwhile to take a look. So for this problem, we know for multiplication, we also have commutative law and associative law. Here, 13 times 25 times 125. If you just follow the given order to do this, it's quite challenging because there's no shortcut. You just need to do the hard work. But if you just have developed some number sense, you should immediately see there are some very nice numbers here. 25, 125, 4, and 8. Why? Because those numbers are so 125 are multiple fives, 5 times 5, 5 times 5 times 5, right? And the 4 and are the multiple of 20. So like 2 times 25 is 50, 3 times 25 is 75, and so on. You probably up to 9 times 25. That will be it. You don't have to continue this forever, but up to 9 times 25, 10 of course is a given. 10 times 25 is 250. So those 9, actually 8 facts should be properly memorized. On the right hand side, those are the multiple of 125. You should also memorize those facts. It's not that difficult. This table is particularly important because when you later study fraction, multiple of 1/8, say 1/8, 2/8, 3/8, say 5/8, 7/8. What are the decimal value of those fractions? Well, if you memorize those facts, you will be just very quick to answer that question. So 7/8 is 0.875. Of course, that's for the future. So back to this problem. Because of those facts, we can see that we can use the commutative and associative law properly so that if we group 25 and 4 together, we get 100, right? And if we group 125 and 8 together, we get 1,000 right here. It's 1,000. So therefore, 100 times 1,000 times 13. That's super easy. You just add a whole bunch of zeros. In particular, you have 100, 1,000, and 225 combined with 4, and 125 combined with 8. How about a problem like this? Well, we have two multiplication problems. In order to do this very efficiently, very fast,
it's not really working. Like it's constantly, like it doesn't really work.
Okay, that's okay. I will upload a video. So you times 37 with 102. 37 times 100 plus 2. The reason is that we like nice numbers like 100. Now we can use the distributive law, because 37 times 100 by distributive law, and then plus 37 times 2. This will become much easier to do, because 37 times 100, that's just 3700. You just add 0 to that. 37 times 2, well, if you are not super good at mental math, you may do it on paper, but in general, those two-digit numbers times any number, you should try your best to do it just in your brain, okay? So this would be 34. Therefore, you can see that 3700, we have 2 zeros here, and this is a two-digit number, so they add up to 3774. Very fast. Actually, this whole thing can be properly performed within your mind, okay? So this is a direct application of distributive property right here. We break it down or rewrite 102 as 100 plus 2. So it becomes the sum of two numbers. Now we use the distribution over the addition to perform this multiplication. And therefore we get this, and each of those two are fairly easy to compute, and the final result is just that. Okay. How about the one in red? Well, we have not formally discussed this yet, because we will introduce subtraction as an alternative version to addition soon, but assuming that you have known, and this is a safe assumption, right? Assuming you have already known subtraction, so you would see that 37 times 97 would be written as 100 minus 3. Just like 102, 97 is also quite close to 100. Therefore, we can rewrite 97 in this way. Now, we have not discussed this yet, but just for your information, so that we don't have to go to this problem once we have already introduced subtraction. So the distributive law actually still works in this case, even with a subtraction part in the expression, because later you will know minus 3, subtracting 3 is really just adding negation of 3, negative 3. So adding negative 3 is exactly the same thing as subtracting 3. Therefore, you can also use associative, commutative, and distributive law with a subtraction if you properly convert a subtracting problem into addition problem. Okay, so this, because distributive law also works in this case, even when subtraction is involved. So this is 3700 subtract. So it's truly, if you want to ask, challenging me why you can do this so fast, well, because I have learned how to perform mental math. That's another thing that you may consider if you truly like math. Okay, so those are straightforward application of the distributive law. Now let's take a little bit more complicated problem. So 4 times 63 times 25. Oops, I think I made a interesting adjustment here. So you can see that this is fairly complicated, right? So let's do it on the paper. So now I'm switching to 4 times, I think it's 63 times 25 plus 25 times 39. How do we do it? Well, now you can see that we need to go through a series of arithmetic here. It's the distributive property in the reverse way. We can actually do so from the left to the right. We call distributive law distribution, right? But if we do it in the reverse way from the right to the left, we call it factoring. Okay? What that means is that if you go back to distributive law earlier, you can see that the last one, L times M plus N equals to L times M plus L times N. And this is from the left to right. But if we consider the very same equality from the right to the left, that means that L times M plus L times N, because the two share common multiplication number, which is L, we can actually factor it out. This is what we call factoring. We can put L outside, then M plus N, which is exactly on the left-hand side. So from the right to the left, we call it factoring. Now, back to our problem here. How do we do this problem? Well, we can see that because we have 25, it's a common factor. So we can put 25 out, then times 63 plus 39. Okay. So at this point, 60 plus 39, you can also see that that is quite close to 100. It's not exactly 100 because to get there, 63 need to plus 37, right? But we have 39. That's 2 more than 37. Therefore, the result of 63 plus 39 is 2 more than 1. So now we can rewrite this as 4 times. Because of the associative law, we can first group 4 and 25 together, and this whole thing will be the second multiplicand, and this can be written as 100 plus 2. Okay? Why? Because 63 plus 39 is not exactly 100, but just a little bit higher. 2 larger than 100. So with the facts, 4 times 25, that's the 100. Now 100 times 100 plus 2, using distributive property right here. So 100 times 100, that's 10,000. And then plus 100 times 200. Therefore, the answer is 10,200. Okay? So, seemingly complicated problem, but with the proper use of the associative and distributive law, we were able to do it in a much more efficient way. Okay, now let's talk about some word problem. Remember, a couple of weeks ago, we discussed a general, quite large family of word problem in which we have 2 quantities, want to determine what they are, and the 2 quantities exhibit certain relationships. And we say that there were 3 fundamental relationships. One is the sum of the 2 numbers, one is the difference between the 2 numbers, meaning that the larger one subtracting the smaller one, difference, and then there's a multiple if it happens. Not necessarily 2 numbers are always one of the multiple of the other, but a lot of times this is the reality. One number is kind of a multiple of a second number. Even it may not be exactly, we can do some adjustment, but generally we are searching for a multiple relationship. So there are 3 such relationships: sum, difference, and multiple. We have 2 numbers. Later on, if you study algebra, you'll see that in order to determine the values of 2 numbers, we need 2 independent relationships, or kind of what we will call equation. But we are not doing algebra, we are still doing arithmetic, so we will not go there. But the point is that we just need to know 2 of such 3 unknown quantities: sum, difference, multiple. If we know 2 of them, we can ascertain what those numbers are. And the particular relationship is that because the large is the multiple of the small, so their sum is just large plus small. That is multiple times small plus small. Therefore, now you can see with distributive property, we can factor out the small, because now you are adding 1 small. So after factoring small, what goes into the parentheses is the multiple, that represents the large number, then plus 1, that represents the small number. And similarly, if we know the difference and the multiples, then we will have this relationship. Still, large is a multiple of small, but now the difference instead of the sum of the 2 is the large minus small. We just mentioned that distributive property, even in this case, still works. So therefore, the difference is a multiple of small. But how many multiples? Is the original large number's multiple subtracting 1. This multiple in red represents the large number. And this subtracting 1 is just the small number itself. So that's why you subtract 1. And this is the so-called the difference multiple relationship. It's a very powerful relationship. So with those 2 properties, we can 2 relationships is really, there's a quantity that's a multiple relationship of the other. And when you including or excluding that small number itself, the sum or difference can result in a plus 1 or minus 1 inside the distribution. So the total age of ABC is 95. Alice, Betty, Carol. Alice is 5 years older than twice the age of Betty. So Alice is fairly kind of just the most senior lady, right? If you think that the Betty's age, twice of the Betty's age, then still need to add 5 more years. That's Alice's age. Betty, however, but don't be discouraged. You have to understand what we just reviewed, the sum difference, the sum multiple, and the difference multiple. The key, you just don't memorize that formula. The key is to find, after some manipulation, perhaps arithmetic, then you find a relationship. One number is a multiple of another number. But this problem, how should we solve that? Well, you just think rough visual aid to solve a math problem. You're kind of taking the easy way, but that's harmful to your mathematical growth. So we try not to do that. So ignore that 5 years old is somehow twice the age of Betty. Forget about 5 years older condition. What is Betty? Betty is 19 years younger than, again, twice the age of Carol. If we ignore, once again, this 19 years younger condition, so now we have a much simpler relationship. That is Alice twice the age of Betty, and Betty in turn is twice the age of Carol, right? What does that mean? Carol is the youngest person, And we can use her age as a base. We already know, pretending we ignored the 5 years and 19 years for now, Betty is twice of Carol. And Alice is twice of Betty. So that means 2 times 2, Alice must be somehow 4 times the age of Carol, right? So if in such a case, even though we have 3 numbers instead of 2, the same relationship with the same concept still applies. Those apply to 2 numbers, still the same here. Because now if you see Carol as the youngest person, we use her age as 1 multiple, just itself, right? 1 times any number is that number itself. Then Betty is twice of her. Simple. Then we should be able to divide 95, which is the total age of the 3, by that 7, which is the total multiple of Carol's age. That would be much easier. But this problem is more difficult because every step of the way, that multiple relationship is not perfect. It needs some adjustment. Although this will introduce some difficulty, we can get around it by every time when say this number is a few digits, just kind of either over or under the basis. Then in that case, we artificially try to make that gap. And what do we mean by that? Just think about it. If Betty is 19 years younger than twice of the age of Carol, what can we do to make Betty's age exactly twice the age of Carol? We imagine somehow Betty get 19 years more age. Meaning that if Betty get 19 years older, her age would be exactly twice of Carol, right? Assume that's a new basis. In that case, well, if Alice wants to be exactly twice the age of Betty, what did Alice need to do to adjust her age? Her starting point is already 5 years older than twice the age of Betty, but that's Betty's real age. If now we want to make Betty 19 years older, what kind of adjustment Alice need to make? Well, because Betty is 19 years older, in order to kind of stay twice the age of Betty, Alice needs to add several years to her age, right? That would be 19 plus 2. Because Betty gets 19 years older, Alice has to match that twice because she wants to stay as twice as Betty's age. So she needs to add 38 years in order to remain as twice old as Betty. But remember, she was already 5 years older than twice. So she did have kind of like she had saving for future expense. She had 5 years already. So all she needs now is 19 times 2, subtracting 5. What is exactly the meaning of this expression? This is the year that Alice would have to be twice of adjusted Betty's age, which in turn is twice of Carol's age. So that way, Alice will be actually 4 times Carol's age, right? Remember, Betty, in order to match Carol's real age, needs to get 19 years older. And as the result, Alice needs to further 19 times 2, get that many years older. Also, she did have a head start advantage. She was already 5 years more than the real Betty's age. Therefore, this is the total year that Alice needs to bring her own age to be exactly 4 times of Carol's age. And in this case, we know Betty also need to add 19 years, right? So essentially, we give this many years to Alice to allow her age to stay as exactly 4 times of Carol's age. At the same time, even just one number, we still use a parenthesis to highlight the concept. 19 is the year Betty would need to be twice of Carol's age. If we make such an adjustment, then what happened? Betty is exactly twice the age of Carol, and Alice is exactly 2 times 2, 4 times the age of Carol. Therefore, this now. So, if we give their total age 95, collectively this many more years, what is this number? This is 147. Okay? This would be the new total age plus 1, where you only have 2 numbers. So now we cannot just be a kind of calculator. Alice, 2 multiples, that's Betty. Carol's age, right? 21. And what is Betty's age? Betty is twice of this, 20. 21 times 2, subtracting 19. Remember, Betty is 19 years younger than twice of Carol's age. So this is 42. 42 minus 19, that's 23. Okay, so Betty is 23. And what is Alice's age? Alice is 23 times 2 and plus 5. So this is 46 plus 5, that's 51. So those are the age of those 3 ladies. Okay, so this problem we see that we learn some standard building blocks like the sum and the multiple, the difference and multiple, but we should be able to extend our knowledge into situations where we need to make some adjustment. That's how you should approach math. Just don't memorize things. Make yourself look like. Take a look at the next number. All right. So we have bucket A contains 15 more gallons of gasoline than the amount of gasoline contained by bucket B. So A is 15 plus B. So this kind of just relationship you will see is exactly what we need to do in algebra. But for now, you just keep this relationship in mind. A has 15 more gallons than B. If half the gasoline in bucket A is poured into B, then B will contain 60 gallons of gasoline. How much gasoline does each bucket currently contain? So we know we have 2 unknown numbers. A's amount of gasoline, B's amount of gasoline, but we have 2 relationships. Except maybe the difference, initial difference, 15, that we know. But how do we translate the statement that if half the gasoline in bucket A is pulled from A to B, then B will contain 60 gallons? Well, you have to think outside the box. The key here is there's a word half, right? Half is not just any given random number. It's a very nice number. You just get 1/2 of A into B. What shall we do now? Well, you have to be clever. Think about it. How can we take advantage of this fact that if half of the gasoline in A is into B, okay, half means that it's 1/2. The inverse is double, right? Now if you imagine B now is 60 gallons, what is that? It's all gasoline, and it contains half of A. How can we take advantage or use that half information? We can double the new updated amount of gasoline in B, right? If we double B, just imagine that after this, B has 60 gallons, right? If we have another gallon copy of the updated B, we have two 60s. Now what happened? If we combine them together, that new number 120 must be 2 copies of B and 1 copy of A, right? Yeah. We have 15 gallons of surplus. We have 15 actual gallons if we put 2 B's together, right? So B is 60. We know this is B. If we times twice, it will become 120. But the original B is just B itself plus 1/2 of A. So after you double this, this should be 2 copies of B and 1 full copy of A, right? And that 1 full copy of A is B itself plus another 15 actual. So altogether, we have 3 copies of B, then have a 1 time actual. That is 15 gallons to get to 120. So therefore, if we subtract this actual 15, what do we get? We should get exactly 3 times B's original amount of gas. So divided by 2 plus 1. This signifies that if we double these 2, there's a 2 copy of B, and this 1 actual copy is from A because we pour all A's gas into this imaginary doubled big bucket amount of B, and A is just hold on, 100, yes, 105 divided by 3, yes, B is 35, okay, and A is 50, right? So 2 times 35, 35 plus 15, that's 50. So A equals to 35 plus 15 equal to 50. And so you can verify if you put 1/2 of A, which is 25, into B, B will become 35. Okay? So this may seem to use your imagination to do some trick. Now we will take a look at our next problem, which is much harder. This is 5079. 2 young boys, Aaron and Albert, they save money in their piggy banks. If they swap their roles, if Albert gives Aaron $40, because in general Aaron will have more money than Albert, so this time Aaron will have 3 times the money Albert has. You can see that clearly Aaron should have more money, right? Because they going through the same. Either I give you or you give me $40. Aaron will become 3 times of Albert, but Albert will only become twice the money of Aaron has. How do we do this problem? Well, first of all, for this set of homework problem, you are supposed to use what we learned, the relevant concepts or trick to solve this problem. Later on, once you have learned fractions, you will be able to see for this particular version of this problem, you can use fraction to solve it, and probably faster. Also, we can twist the problem a little bit to break the application of fraction because it depends on those specific cases, but we don't discuss this later. Just want you to know, later we may give you this problem again, but ask you to solve it with fractions. Okay, now what happened? Well, this is very hard to visualize in mind, but this is where you can use some visual aid. So this is Aaron, this is Albert. So we have two sets of conditions. One is that if Aaron gives $40 to Albert, then Albert is twice of Aaron, right? On the other hand, if we do this, if Albert gives $40 to Aaron, this will result in a 3 multiple relationship. We have two unknowns, the amount of money, and two relationships. That in general tells us that this should have a good solution. And looks like this is related to the trick we learned, right? We have two quantities, there's a certain relationship, and one of them is a multiple relationship. But we know how to do. Of course, we just learned the special relationship between two quantities, sum, difference, and multiple. This sounds like that, but it's still not there yet. How can we properly choose a smaller number, which we also call base, to figure out that there's a relationship to solve this problem? Well, in this case, it looks like both Aaron and Albert should be the base, right? But there are two separate conditions, and we don't see any direct connection between those two cases. So even so, in either case, one person can serve as the base for the other, but they're just on two isolated islands. We cannot find a path to connect them. It's just all water in between. That's bad. So if you have already tried this a little bit, you should think of some alternative. You have to be able to think outside the box frequently. So in this case, wait a second. If this guy is twice of, if this guy Albert is twice of Aaron, but Aaron is 3 times of Albert, that sounds like weird, right? I'm twice of your money. You are twice 3 of my money. Let's start with Aaron. That doesn't mean that Aaron is 2 times 3 equals to 6, which is Aaron is 6 times the money of itself, himself. That piggyback, Aaron would be roughly 6 times of itself. But that doesn't sound reasonable. How can you be 6 times of yourself? Of course, the real reason is that they were giving money to each other, so that changed the exact multiple relationship. Just like in the early 2 problems, when we have the 3 ages, A, B, C, Alice, Betty, Carol, now the age is not exactly the multiple, but that's fine. Either plus or minus, we can keep our brain just tracking that information, make that adjustment. If you're 5 years short, we give you the B. So, how do we approach this? So let's choose the small number properly, okay? Let's consider, say, Aaron. When will Aaron be her 6 times of her own money, his own money? We have to choose time when Aaron has the least money, right? Because that's how you measure Albert as twice of Aaron. It's after Aaron gave $40 to Albert, not when he just started. If we choose that one, we'll see at that moment, Albert, after receiving $40 from Aaron, is twice of Aaron's money. But now, how about the other condition? Say, Albert gives Aaron $40. But you should think of that situation from the first verse that Aaron gave to me, if I'm Albert, right? This will restore our $40 calculated from the moment when Aaron just gave $40 to Albert. And from that point on, our Albert will effectively give $80 to Aaron in order to create this case. What we say, Albert gives $40 to Aaron. Does that make sense? Effectively, you are giving $80 because the $40, the first $40 is to reverse Aaron's gift to you. That way, we will be exactly at the same case as described in the problem. Giving $40 to Aaron is really giving $80 back to Aaron if you have already received $40 from Aaron. So why this is important? Because we have to do this to properly align or track the numbers we are trying to figure out. Okay, so after Albert effectively gives $80 back to Aaron, what happened in that case? Albert's money goes down by $80 as measured from the moment when Albert was the richest, right? After getting $40 from Aaron. At that time, it was the richest a moment for Albert. Then money goes down by $80. But Aaron's money goes up by $80. And this time it's 3 times of Albert. But remember, these 3 times is not what we want. We want 3 times as measured when Albert was the richest, right? When Albert just got $40 from Aaron, at that moment, Albert was at a historical high. We want to use that as the basis, just like the Alice Betty Carroll case, right? So, how do we achieve that? Because now the 3 times after this $80 down. How about say Albert did not incur $80 just loss? This case will give just a giving away. Then we need to restore Albert's money back to when he was richest. So we have to hypothetically just imagine we are giving Albert $80 back, so that he will be at that highest point, which will be exactly twice of Aaron's low point, right? We want to track apple throughout the course. We don't want some orange along the way. If we have orange, we just do some patchwork to make the orange looks like apple. Okay? All right. So in this case, we need to artificially, hypothetically give Albert $80 back. And if in that case, Aaron wants to continue keep this 3 times relationship, Aaron need to go up by 80 times 3 equals to $240. This is how hypothetical happened, right? So in this case, if we restore the $80 for Albert so that Albert will be back to at his high point, Aaron needs to have 80 times 3 times that much more money in order to keep pace with Albert. So the keep pace meaning that Aaron wants to stay at 3 times of Albert's money. So you need that much money. If let's just say at that time this happened, Aaron, after receiving the $80 from Albert, get another $240 to Albert. At that point, Aaron had the lowest money, and that money becomes 6 times itself, but only because some interesting transaction. First, Aaron received an $80 payback from Albert, right? He got $80 back. Now, he needs to imaginarily have another $240. So that is Aaron in total need to be $80. This is the money Albert gave back to Aaron plus 80 times 3. And this is the imaginary actual money in order to keep the pace as Albert's. So Aaron's money needs to be this much more than when he was the poorest, right? After giving $40 to Albert, that time he was the poorest. From that point on, he needs to first get 80 from Albert, then get 240 imaginarily. The only reason for tracking this number is that at this point, Aaron will be 2 times 3 times, exactly 6 times of itself. Remember, this is his starting point. Just 80 plus 80 plus 240 will be 6 times of this poor status. And this is a difference multiple problem, right? From one multiple, you get 80 more and 240 more, then becomes 6 times of yourself. We took pain to make sure that this 2 times 3 is valid, because every step of the way, if the multiple is not perfect, we make some adjustment to make it perfect. But that way you need to get something like this, okay? So this represents 5 times, because 6 minus 1, right? You have to subtracting 1, subtracting yourself. This is the 5 times multiple of Aaron's lowest point money. So this is 320 divided by 6 minus 1. And to be more exact, 6 comes from the fact that 2 times 3 minus 1. This is 5. So Aaron's money, this is 320 divided by 5, that's 64. What is 64? 64 is when Aaron was the poorest after he gave away $40 to Albert. So initially he should have 64 plus 40 equals to $104. That's the subtract 40. And this is 128 subtracted 40 equals to 88. So initially Aaron had 40 to Albert, Aaron becomes 64, and Albert becomes 128. That's exactly twice. Okay, so you can see that this problem is actually built upon kind of the earlier Alice, Betty, and Carol's problem. Okay? That's it for today. There's one more problem. We don't have time. That's the extension of 180. Very similar with a little bit twist to make it a little bit more complicated. But if you do understand how we solve the 5.079, you should be able to solve this problem as well. If you have not done it yet, give it a try. Very challenging, but if you figure out from beginning to end how the reasoning works, I'm pretty confident you will learn a lot. Okay? And this is exactly how we should train you about just to think, just to get hands dirty, do the actual problem. If you struggle for an hour for this problem, that's perfectly normal. Cannot be more normal than that, because this is a very difficult kind of problem. All right? I'm sorry for the technical difficulty happened earlier. I will take a look at YouTube to see if the video is okay. But I believe in any case, I have some local copies. In any way, I may have to do a little bit just a video work to stitch the pieces together. Hopefully, it still looks like a normal lecture. All right? Thank you. Bye-bye.